Good morning, all of you. We were discussing crystal systems. Now, the next crystal system is rhombohedral. That is the fifth crystal system. Crystal system 5. That is rhombohedral. First one what we learned was cubic. Now you consider that cube. Consider this cube. I am drawing this cube. This cube you press from all the sides. You press from all the sides means you can press from this side and the front side together with this side. From this corner you can press. Then what will happen? This will be moving to one side. It will be shifting to one side. For example, I am showing towards right hand side. Now you see that cube has got turned to that right hand side. Edge lines are the same, that is A is equal to B is equal to C. Here no angle is 90, but here all angles are equal. If all angles are equal, that is alpha is equal to beta is equal to gamma, but they are not equal to 90. All got tilted to right hand side. The same cube we tilted to the right hand side. So what happens? All angles are equally, and which is not equal to 90. Since it was a cube, A is equal to B is equal to C. This has got only one variation, that is primitive. Primitive means only at the corners. Only one variation. This corner, this corner, this corner, this is primitive. You can locate 8 atoms. You can locate the position of 8 atoms. Example is cinnabar. Cinnabar, that is HGS. If you take HGS, that HGS crystal lattice will be made up of such unit cells, primitive unit cells. Another example is calcite. Calcite, that is CaCO3. So this is the fifth crystal system, rhombohedral. It is actually obtained by pressing this cube. That was the first crystal system. Only primitive is there. Primitive. Now next crystal system is, that is the sixth crystal system, monoclinic. Monoclinic, that is crystal system 6th, means 6th shape we can say. Example is monoclinic sulfur, and another example Na2SO4.10H2O. So for that I am inviting towards that matchbox. What was matchbox? I am drawing that matchbox and we will be pressing the matchbox from one side. Matchbox was like this. In Matchbox, A is not equal to B, which is not equal to C. All the angles were equal, but if I press from this side, I'm not moving this dotted area. This dotted area is a rectangle. The dotted area is not moved. Only this dashed area is pressed. For example, towards the right hand side I pressed. I am not moving the dotted position, dotted rectangle. So here dotted rectangle, it is 90 only. This is 90 only, right? And the side which is dashed, that is just turned. Again, this angle is 90 only, that is not changed. Which angle is changed? This angle is changed, that is beta is not 90 now. So I am drawing that. So matchbox is pressed from one side. So this angle, that is this angle, I am not moving this dotted area. Dotted area was rectangle only. But this dashed area, this area, that has gone to the right hand side. So this angle changed. When I press from the dashed area to the right hand side, what happened? The angle beta, that is not equal to 90 now, that is not equal to 90. But this which was not moved, that is 90, and here that is also 90. So I am writing that is beta is not equal to 90, alpha is equal to 90, and gamma is also equal to 90, and beta is not equal to 90. Since it was matchbox, now A is not equal to B, which is not equal to C. So this is monoclinic. Example is monoclinic sulfur. Example is monoclinic sulfur. Monoclinic sulfur. Another example is Na2SO4, means hydrated sodium sulfate dot 10H2O. In this we have two variations. One is primitive and the other is end-centered. This is primitive. This is one variation. And in the same thing I am showing the second variation, that is end-centered. This is in addition to this primitive, in addition to this corner ones, if you have on the center of opposite sides, then we call it as end-centered. So two variations are there. Next, last crystal system, that is seventh shape, last crystal system. 7. that is called triclinic. Triclinic. Here A is not equal to B, which is not equal to C, but I am drawing that. You can draw in any format. That is, A is not equal to B, which is not equal to C, and all angles are different. Alpha is not equal to beta, which is not equal to gamma and not equal to 90. So you can draw in any format. This is triclinic. The conditions are A is not equal to B is not equal to C, and all angles are also different. Example, K2Cr2O7. K2Cr2O7, that is potassium dichromate, orange crystals of potassium dichromate. Thus, there are 7 crystal systems. 7 crystal systems. In this, only primitive is there. Only primitive. Only at the corners. No body center, no face center, no end centered, only primitive is there. So there are 7 crystal systems, and we can see what all variations in each crystal system. So first one, cubic. In cubic, primitive, body centered cube, face centered cube. In tetragonal, so here 3 variations are there. 3 variations are there. In tetragonal, primitive and body centered. That means 2 variations are there. In orthorhombic, primitive, body centered, face centered and end centered. That means 4 variations are there. Primitive 1, 2, 3, 4. In hexagonal, only primitive. In rhombohedral, only primitive. In monoclinic, primitive and end centered. In triclinic, only primitive. So here 1, here 1, here 2, here 1. So here 5, then 10, then 14. All together 14 variations are there. In these 7 crystal systems, all together there are 14 variations are there. We say there are 14 brevis lattices. Brevis lattices. There are 7 crystal systems. There are 7 crystal systems plus along in 7 crystal system different variations are there. All these variations together we call 14 brevis lattices. Okay, so there are 2 types of unit cells, primitive and center. Next we are going to see the number of atoms in a unit cell. In a unit cell means that is in cubic, that simple cube, body centered and face centered. So simple cube, body centered and face centered, we are going to find the number of atoms in a unit cell. We will be dealing with first simple cube. We will be dealing with simple cube, BCC and FCC. So first one, simple cube. I am drawing a simple cube. In simple cube, that means primitive one. In primitive one, you see atoms only at the corners. So here one atom, here one atom, here one atom, 8 corners, 8 atoms. Look at this atom, what I am shading. This atom, you see, only a part of this atom is in this particular cube. How much is in this cube and how much is outside? For that, I am going to draw a crystal lattice. In this crystal lattice, what I have shown here, that I am going to highlight it. This unit cell. What I have shown above, that is this cube. Now, what I have shown here, that is at this corner, the shaded circle, yes, shaded sphere, that is present here. That means, of this sphere, only 1/8 portion is inside this unit cell. Actually, this sphere is divided into 8 cubes, 8 unit cells. One unit cell I have shown here. To this unit cell, on the right hand side you see one unit cell. Behind this unit cell, another unit cell. Diagonal to this unit cell, another one. So you can see 8 unit cells in this to make this crystal lattice. And the shaded ball, the shaded sphere or shaded atom that is seen here, that is divided into 8 cubes. Contribution of that sphere to this particular unit cell is only 1/8. Rest 7/8 in other unit cells. So what is the contribution of a corner atom to this particular unit cell? That is only 1/8. Similarly here, from here 1/8, from here 1/8, this corner 1/8, this corner 1/8, this corner 1/8. So like this, 8 corner atoms are there, 8 corner particles are there, 8 corner atoms are there, atoms, ions, whatever it is. From these 8 corners, only 1/8 portion from each corner atom, only 1/8 is there in this particular unit cell. So 1/8 from this, 1/8 from this, 1/8 from this, 1/8, 1/8, 1/8, 1/8. Like that, 8 into 1/8, that is only one atom is present in this particular unit cell. This is the case of primitive, that is simple cube. So what is the total number of atoms in a simple cube? That is 1 atom. Though you are counting 8 atoms, but inside this unit cell only 1 atom is there. Only 1/8 portion of each sphere, each ball, each atom is present in this particular unit cell. So the total number of atoms in this unit cell is 1. What about BCC, body centered cube? Now, in addition to these 8 corner atoms, there is one atom at the interior center. I am changing the color, but it should be the same atom only. To make you understand, I am changing the color. Otherwise, I would have shown with the red only. This interior center. At the interior center, right at the center, there is one atom. So at the interior center, there is one atom. Its contribution to this particular unit cell is 1 full. You see? So BCC means, in addition to the corner atoms, 8 corner atoms, there is one atom at the interior center, body centered cube. This is not actually black in color, it is red in color only. To make you understand where is its location, I am drawing like this. So its contribution is full, and this is also there in BCC, 8 into 1/8. From the corner contribution, this is only only 1/8 from here, 1/8 from here, 1/8 from here, 1/8, 1/8, 1/8, all the corner 1/8, 1/8, and this is 1 full. So this 1 plus 1, that is 2 atoms are present in body centered cube. Now let's come to face centered cube. So number of atoms present in simple cube, primitive. Number of atoms present in that simple cube. Actually these edges are imaginary edges. We call it as edge length. Imaginary lines drawn, edge length. So in the case of a simple cube, the total number of atoms is 1. In the case of BCC, body centered cube, the total number of atoms is equal to 2. Now, what about FCC? So, for FCC, corner atoms are there, but the center, I am going to remove that center one. In addition to these corner atoms, I am going to draw the same atom at the center of each face. I should have done with a red color only. To make you know the location, I am changing the color. Here, center of this face, same size, center of this face. How many faces are there? 6 faces are there for the cube. Center of top face, center of this side face, now bottom face center, and this side face. Now one face is there in front, that is front face, and the back face. Okay, so here 6 atoms you can see. These all are to be drawn with the red only. To know the location, I am showing with this black color. Look at this one. Look at this blue dotted one. Actually, half of this ball, half of this sphere, half of this atom is present in this particular unit cell, and half is in the upper unit cell, that means this unit cell. One half in the down unit cell, and the upper half is in this unit cell, what I am highlighting with the blue. So, the contribution to this particular unit cell, highlighted unit cell with red, that is only half. Similar is the case with this one, half. Half is to this particular unit cell, half is to the right hand side unit cell. From this also, from the face center, only half contribution is there to this particular unit cell. So, from the top half, bottom half, right hand side half, left hand side half, front half, back half. So, how many halves are there? 6 halves are there. 6 halves means that is 6 into half, that is 3. In addition to that corner, that is 8 into 1 by 8 is equal to 1. So, total number of atoms, all atoms are red atoms only, all are red atoms only, all are red particles only, same atom, corner same atoms, center of each face same atom. Now, 8 into 1 by 8, 1, 6 into half, that is 3. So, 1 plus 3, altogether 4 atoms are present. In face centered cube, this is FCC. FCC, what I have shown here, this is FCC. Like that, other cubes are also in FCC only. In this crystal lattice is made up of FCC unit cells. So, the number of atoms present in FCC is 4. Once again, number of atoms present in simple cube is 1. Number of atoms present in BCC, total number of atoms present in BCC, that is 2. Number of atoms present in FCC is 4. We represent this number of atoms by the letter Z. For Z is equal to 1, simple Q. Z is equal to 2, BCC. Z is equal to 4, FCC. So these are the total number of atoms. Next class we will be doing packing efficiency. Thank you.